So form of Van Hoff's equation is so the full form of the equation is Kc at your new temperature is going to be your reference temperature, equilibrium constant times exponential of negative delta H over R times 1 over your T2 minus 1 over T1, and then minus this delta times your natural log of your T2 over T1. Normally, the delta H of reaction is large enough that you can say that this delta natural log of T over T2 over T1 is negligible. So for Weaver's test, I think he gave extra credit if you stall for the delta term too. But as long as you state your assumptions, I think he gives you full credit. So I just wanted to point out that usually, like hallmarks and things, I don't bother using this, but it's still there. And this problem actually does make a difference. So let's go back over here.
What is that delta term?
What is the delta term?
The summation of the coefficient in the Van Hoff.
In the Van Hoff. So I think it's just taking into account change in the, like any kind of change in moles of from resulting in the reaction from the or in the volume from the reaction that'll affect your Kc. But normally it's negligible to the heat of reaction. Depends on how precise you want to be. Yeah.
Is the delta term in the exponent?
No, I just ran out of room.
Okay,
So it's, I can rewrite it if you want. So this exponent term so this is the exponent term. So it's negative delta H over R times the difference over 1 over T minus 1 over T1. And then that is minus delta natural log of T2 over T1.
Is the delta term an entropy term?
It could be. I honestly don't remember. It's been a while. It's, so again, it's normally not used, but depending on how precise you want to be, can make a difference.
So is it in the exponent or outside of it?
It's an exponential.
Okay.
Sorry.
So it's not the same delta we saw. The-
I
It is in
believe it is the same delta.
Same,
Yeah. So this accounts for a change in moles, which, I mean, if you have 0, then that term goes to 0 anyway. So if you choose to keep the delta term, your Kc at 600 is 0.016 moles per liter. That's with delta. But if you don't, and you just assume that delta H is much larger than that term, then your Kc at 600 is double, so it's 0.033. So this ends up making a difference in the conversion. So now that you have this Kc, you can go back, you know your C and I, gives you C and I. You know your T 600, T naught 300, for KC, so you can solve your equilibrium conversion. And depending on which one of these you use, it's either going to be, so for this one, your equilibrium conversion will be 0.63. But if you use the 0.016 term for KC, your equilibrium conversion comes out to be 0.5 exactly. So in this case, it did make a difference, but again, as long as you state your assumptions, it doesn't matter what you use, you get full credit. So that was the first part of the part A, so solving for the equilibrium conversion. So then you have to solve for the real conversion, which you get from your energy balance. So your energy balance is going to be 0 equals negative CPA T minus T naught. So this problem is in an adiabatic reactor. So this is your energy balance equation. You just rearrange for x and use your known parameters. And your real conversion comes out to be 0.225. So significantly lower than either equilibrium conversion. Did everyone get everything over here? So, so part B, it gives you a plot on the back page, and the part B asks you to sketch the corresponding energy balance curve on figure 1 and estimate the adiabatic temperature and conversion from the graph for the feed conditions given. So you know KC at 300, KC at 600. So you can go, and you know the conversions corresponding to these two. So 300, you get 0.225. Can't even draw on curve, right? So 600, it's going to be, not drawn the scale, it's going to be, what is it? Oh, I'm sorry, 600 is 0.225. And at 300, that's 0. So you can just draw this line out to the equilibrium curve. And from here, you can just draw down. And you'll get some temperature, and you draw over, and you get some conversion. So basically, use the points you have, so the 300 and 600. Draw a line out until it intersects the equilibrium curve, and then whatever temperature and conversion that is your answer.
Could you repeat the question?
Yeah. So to sketch the corresponding energy balance on the curve on figure 1 and estimate the adiabatic temperature and conversion from the graph for few conditions given. So the adiabatic temperature and conversion are going to be where it intersects the equilibrium curve. And yeah, the energy balance is just using your points. So you have your point 225 at 600 over here, and you can assume 0, 300, and just draw a line out to intersect the equilibrium curve. That's your adiabatic operating temperature. So does that make sense?
No.
Perfect.
The linear line is the energy balance, and
Yeah.
the other line is the equilibrium curve.
Right, so the curve 1 is the equilibrium curve. So that's what it gives you. And then you solve for a point for energy balance here at 600 and at 600 Kelvin, 0.225 conversion. So that's your first point. And then your second point is going to be the initial condition where there's no conversion, so 0 at an inlet temperature of 300. So then you have 2 points. You connect those 2 points. It's got to be linear, so it's aligned. Draw it out till it intersects the equilibrium curve at adiabatic temperature with an equilibrium reaction. The only point where it's going to be adiabatic is when you're at that equilibrium. So then, from where the energy balance intersects the equilibrium curve, that's going to be your adiabatic operating temperature and conversion.
It may just be the way you drew it, but for what was actually given is the equilibrium line closer to our equilibrium values at T for 600.
Yeah, so it'll come out to be around these. So I just drew a really shitty curve. It's not on the scale. But yeah.